Hello, brilliant minds. Have you ever wondered why light sometimes just bounces back completely instead of passing through? It's like when you throw a ball at a wall at just the right angle and it bounces straight back. Light loves doing that too. This magic trick is called total internal reflection, and it happens when light moves from a denser medium like water or glass to a rarer one, such as air, and the angle it hits the boundary with is bigger than something we call the critical angle. Now, let's play detective and derive the critical angle using Snell's law. Don't worry, it's simpler than it sounds. Imagine light traveling from a denser medium, say medium 1, with refractive index N1, to a rarer medium 2, with refractive index N2, where N1 is greater than N2. According to Snell's law, N1 times the sine of the critical angle C equals N2 times the sine of 90 degrees. Since sine of 90 degrees is 1, this simplifies to sine of C equals the ratio of N2 divided by N1. So, mathematically, the critical angle C equals the inverse sine or arc sin of N2 over N1. For example, think about glass with a refractive index of 1.5 and air with about 1. When you calculate the critical angle, it comes out to around 41.8 degrees. Anything beyond this, and light refuses to pass into the air, it just bounces right back. But here's the catch. If the refractive index of the first medium is less than or equal to that of the second, no critical angle exists, and total internal reflection cannot occur. So, water and glass interface? Possible. Air and water? Nope, doesn't work the same way. Picture a graph where the x-axis is the incident angle I and the y-axis is the refraction angle R. As you increase I, R also increases but never exceeds 90 degrees. The point where R hits 90 degrees, that's our critical angle C. Alright, let's dive into what exactly helps total internal reflection happen and what messes it up. First off, the essential condition is that light moves from a medium with a higher refractive index to one with a lower refractive index, and it hits the interface at an angle bigger than the critical angle. Materials are like personality types. Some are more prone to encourage TIR. When the surface of the medium is beautifully polished and smooth, light bounces nicely without scattering, similar to a smooth dance floor making dance moves easier. Rough surfaces are more like a bumpy road that scatters light and spoils the reflection show. The shape of the surface matters too. Flat surfaces reflect predictably, while curved surfaces can focus or deflect light in complex ways. Think of optical fibers, which are like super thin light highways where light zigzags inside due to total internal reflection. Also, how the light rays spread affects TIR. Collimated rays, those beautiful parallel beams, like from a laser pointer, maintain their path better than scattered rays. That's why devices like endoscopes and prisms rely on controlling edges and surfaces meticulously to guide light efficiently. In the diagram, you can see rays approaching the boundary from the denser side at different incident angles. Those below the critical angle partially escape by refraction, but those above it get completely reflected back, demonstrating the magic again. Here's where total internal reflection gets really exciting. It's the secret behind some of our coolest gadgets. First up, optical fibers, those tiny strands that power your internet and phone calls. Light signals inside these fibers keep bouncing off the inner walls completely thanks to TIR, allowing data to travel vast distances with almost no loss. Imagine a light beam trapped inside a long glass tunnel, pretty futuristic, right? Then there are prisms, especially the 90-degree, 45-degree, 45-degree ones, which use total internal reflection to bend light beams cleanly without absorption losses. This makes them perfect for binoculars and periscopes, which redirect and erect images so we can see faraway things clearly and right side up. Even diamond cutters know this trick. By shaping the diamond to maximize internal reflections, they trap light inside, making them sparkle with that jaw-dropping brilliance. It's like playing a light game of hide-and-seek inside the gem. In the schematics, you see light entering an optical fiber and bouncing repeatedly inside, never leaking out. Also, prisms shaded with precise angles show light rays reflecting internally at perfect angles, redirecting beams right where we want them. Let's solve a real problem to bring theory to life. Suppose we have glass with a refractive index N1 equal to 1.5 and water with N2 equal to 1.33. What's the critical angle for total internal reflection at the glass-water interface? Using Snell's law at the critical angle, sin of C equals N2 divided by N1, that's 1.33 divided by 1.5, which equals approximately 0.8867. Now, applying the inverse sine function gives C equals arcsin of 0.8867, which is about 62.46 degrees. This means that whenever the angle of incidence in glass exceeds 62.46 degrees, light will totally reflect inside the glass instead of going into water. Imagine being a light ray trapped inside glass, no chance of escape beyond this magical angle. The simple ray diagram shows the boundary between glass and water, marking the angles involved, helping you visualize exactly where total internal reflection kicks in. To wrap it up, total internal reflection happens when light travels from a denser medium with refractive index N1 to a rarer medium with refractive index N2, and the incidence angle exceeds the critical angle C, which equals the inverse sine of N2 over N1. This phenomenon is harnessed ingeniously in optical fibers, prisms, binoculars, and even to enhance the sparkling brilliance of gemstones. Importantly, in ideal conditions, there is no energy loss to refraction since all the light reflects back, making TIR an efficient and powerful tool in optics. So next time you see a diamond sparkle or use a pair of binoculars, remember the light is bouncing inside, refusing to escape, all thanks to total internal reflection. That's all for today's journey through the fascinating world of light's hidden bounces. Physics is fun when you can laugh and learn. See you in the next session.